Okay, so now we'll look at projectile motion. And projectile motion is an object moving only under the influence of gravity. Air resistance is negligible, and this motion happens in two dimensions. Motion in two dimensions. So motion is under the influence of gravity alone, and the acceleration is constant over the range of the motion. So for instance, if you threw an object that went 500 miles into space, g would change, and that would not be a projectile motion. And what you learn is that the trajectory of this particle is a parabola. Now for projectile motion, the horizontal and vertical motion are independent of each other. The trajectory is always a parabola. Okay, so here's a ball that was thrown, and it's moving under the influence of gravity. And one of the things you want to notice is, since the acceleration due to gravity is a vector like that, and that is equal to, it has no x component, and the y component is g, which is 9.8 meters per second squared. Okay, so since the object has no x component of the acceleration, the x component of the velocity of the object does not change, it remains constant. It has a y component of acceleration, and so the y component of the velocity changes, and the y component of the acceleration is a negative. So when you have positive velocity, that's decreasing, and then eventually you get a velocity in the negative y direction. Okay. All right. So what this slide does is, you know that the equation of a parabola is y, which should be a quadratic function of x if this is a parabolic trajectory, and that's what this slide is showing you. Y is a quadratic function of x, and since the quotient of x squared is negative, the parabola opens downward. Okay. Now, oftentimes we are interested in, when you throw a projectile, you are interested in the range of the projectile. The range is the horizontal distance it travels when it's come back to the same vertical location. Okay, so when it's so if you throw an object from ground level, it's hit the ground again. If you're throwing it from the top of a building, the projectile would keep going, but the range would correspond to this distance when it's come back to the same vertical position. Okay, and the range is given by the speed square, the initial speed of the object, and so theta naught is the launch angle. So sine 2 theta divided by g. So that's the range of the object. We are also interested in what is the maximum height the object would reach. And the maximum height is given by speed squared times sine squared theta divided by 2g. Now, most of you know that you can throw an object the furthest if you throw it at an angle of 45 degrees. And you can see that from this formula. The range would be maximum for a given speed if this is fixed and this is fixed. For a given speed, the only thing that can change is the launch angle. And the maximum value this function can have is 1, and that happens at 90 degrees. So this would be 90 degrees, meaning this would be 45 degrees. So you get maximum range at a launch angle of 45 degrees. So here is a projectile motion. You just learned that this basketball goes on a parabolic trajectory. Now, here's another thing. It turns out that the range of complementary angles, so the range of 75-degree launch angle and 15-degree launch angle are the same. The range for 60-degree launch and 30-degree launch are the same. So complementary angles will have the same range. Okay. Now, of course, when you play a sport or something like that, baseball for instance, most balls have most balls in flight have a spin associated with them. So, for instance, a ball with shown are actual trajectories of baseballs that result because of air resistance and top spin. So a ball with top spin would feel a downward force, and it falls to the it hits the ground a lot faster uh, than the parabolic trajectory. Now we'll look at uniform circular motion. We are looking at an object going in a circle at constant speed. So the magnitude of the velocity vector is constant. So here's a drawing of something like this. Okay, so here you're looking at it, this object, and this object is going in a circle counterclockwise, and you see the magnitude of the velocity is not changing. And it turns out that but the velocity is changing, and what is changing is the direction of the velocity. And when only the direction of the velocity changes, the acceleration is perpendicular to the path. And this is known as centripetal acceleration. And at any instant, the acceleration is pointing toward the center of the circle on which this object is going. And so that's why it's called a centripetal acceleration. And so when the object is here, the acceleration would be there. When it's here, there. When it's here, it would be pointing always toward the center. And the magnitude of this acceleration, the length of this vector, the magnitude of this acceleration is given by v squared, the speed of the object square, divided by r. And so the smaller the circle, smaller the radius of the circle, the greater the acceleration. The faster you're going, the greater the acceleration. Okay? And of course, so you'll have to have some kind of force that's directed in that direction to make the car go in a circle. And that force is provided by the friction in the tires, friction between the road and the tires and the road. And obviously you couldn't go too far, because if you exceed the friction force, then you end up going in a straight line and you skid. Right, these slides prove to you that the acceleration is pointed toward the center, and that its magnitude is given by v squared by r. Okay, so that's what these slides do. Okay. Now, if you go to this simulation, what you can see is you can see a simulation where an object is traveling along this curved path, and you can give it a tangential acceleration. A tangential acceleration is its speed is changing. Okay, and if it's going around a curve, then the direction of the velocity vector will also change, and then you'll have a radial acceleration. When the path is straight, the direction is not changing, so you will not have a radial acceleration. But if your speed is changing, you'll have tangential acceleration. So this simulation shows you how motion would look when it has both radial and tangential acceleration. Now, we'll be interested in relative motion. So the thing we're interested in is the following. So let's say here's an observer, and here's an observer in a car that's moving at constant velocity relative to this observer. Here's another observer also moving at constant velocity. What we want to see is what do these two see? How are the things that these two see related to each other? Okay, so for instance, if I throw a ball, what we want to do is we want to relate what she sees and what this person sees. Okay. All right, so here's how we do it. Here's a frame of reference. You can think of it attached to her, and that frame of reference is at rest. And frame B could be attached to this car, which is moving at constant velocity, like that. All right, so let's say this is a bird, and she sees the position of the bird, RPA, and this person sees the position of the bird as RPB. Okay. And that's what this is, RPA, the position of the bird is according to the person standing on the ground, and RPB is the position of the bird according to the person in the car. And so this vector is this vector plus this vector, RPB plus RBA. Now, a way to remember this is, so the subscript, this is position of particle P with respect to A, and you can insert a letter. So we've inserted a letter between P and A. So this is RPB plus RBA. That's a good way to remember. And if you take the derivatives, what this equation is telling you is this is the velocity of this bird with respect to A, and that's equal to velocity of the bird with respect to B. That is, the velocity as seen by the person on the ground, and the velocity of the bird as seen by the person in the car, plus the velocity of B, frame B, with respect to A. So that would correspond to velocity of the car with respect to the ground. And then if you take another derivative, what you see is that the accelerations are the same. As long as this frame is moving at constant velocity, they both see the same acceleration for the particle. Okay, and that's important. All right, so here's an example of this velocity addition formula, and you can look at it. So if you're standing on the ground and you see the rain falling straight down, the person in this car that's traveling toward the right will see the rain falling like so. Okay. So this would be the velocity of the rain with respect to the ground plus velocity of the car with respect to the ground, which is negative of the velocity of the car, and that would be the velocity of the rain with respect to the ground. So again, velocity of the rain with respect to the car is equal to velocity of the rain with respect to the ground plus velocity of the ground with respect to the car. So okay, rain with respect to ground, this is the vector that's straight down. Car with respect to ground is in that direction. Velocity of car with respect to the ground is that direction. So the ground is with respect to the car is going in that direction, which is okay. And there's the velocity of the rain. So velocity of the rain with respect to ground, velocity of ground with respect to car, and that's the velocity of the rain with respect to car. So anyway, there's a lot of notation, but this is what the person driving in the car sees, the rain coming into the windshield. All right.